Today we are going to look at how to do spectral synthesis in Max MSP. In this patch I'm using a spectral analysis of a singing bowl. This is a gong-like sound that contains both clashing and harmonious tones coming together. I'm using this analysis in my patch not only to recreate and resynthesize the sound itself, which I do through 83 individual sine wave oscillators, but also to use the individual partials for other kinds of sounds, a constant soundscape, a new timbres, or variations on the existing timbres of the sound by direct manipulation of its component sine wave partials. This is a fantastic gateway to the world of spectral sound design and spectral thinking. A lot of spectral compositions use these kinds of ideas, the individual tones, the building blocks of specific sounds as a basis for musical creativity. So we are going to be looking not only at multi-channel objects and some jitter applications, but also at how to analyze these kinds of sounds and how to deal with very complicated data sets in the world of Max MSP. So let's start. Okay, what do I need to do to achieve spectral synthesis? Well, there are 3 steps to this, or I'm going to talk about this in 3 steps. So step 1 is to analyze an audio file for sinusoidal partials. No worries if you don't know what sinusoidal partials means yet. The point is we can take any kind of audio file such as samples or even complete pieces or songs, etc., and we can analyze it for simpler sound waves, simpler sine waves that we can put together to resynthesize our audio file. That's what sinusoidal partials means. It means simple sine waves, a collection of sine waves that we can put together to resynthesize the original audio file, so the sample or the piece or the song, etc. Then, number 2, we have to represent this analysis in a way Max will understand, right? So we have to export this analysis and we have to work with the text file so that we can import this in Max. And for this, we are going to be using the call object, short for collection. And this is going to be a collection of all the individual partials of our analysis. So we can either play them together or play them separately or manipulate each partial in any way that we want. And finally, step 3 is going to be, this is the most fun step, resynthesize the audio file using multi-channel oscillators. Very exciting, and this will let us play with the resulting sounds. Right, so this for me is the most important part of all of this, of spectral synthesis, because if we just resynthesize the audio, it's not that different than just playing the audio file itself. But if we do spectral synthesis, if we resynthesize the audio file by playing the sinusoidal partials, well, then we can play with the resulting sounds, which is pretty cool. Okay, so let's start with step 1, analyzing an audio file for sinusoidal partials. And for this, we are going to make use of another application, something else than Max MSP, and this is called Sphere. Right, Sphere is an application for Mac OS as well as Windows, and I believe, yeah, Sphere is short for sinusoidal partial editing analysis and resynthesis. It's not a very exciting name, hence the shortening of Sphere. So this is a super useful app, especially if you're into anything spectral composition or spectral analysis or spectral sound design, because it lets you represent, edit, and save sinusoidal partial analyses of sound files, which is exactly what we need. So you want to go to downloads and download it either for Mac OS or Windows or Mac OS or Mac OS. After you have installed it, you're also going to need some kind of audio file to work with. Again, a sample, a song, or whatever. It can be something you have recorded or something you have downloaded off freesound.org, a very useful website for downloading and finding specific samples. So for this video, I'm going to use this Neptune singing bowl. The person who made this claims that we are going to be listening to a single sound from this person's collection. I imagine a singing bowl frequency of the planet Neptune, which apparently sounds like this. Alright, so we can spectrally analyze and recreate the frequencies of the planet Neptune Again, apparently I have no idea what the frequencies of planet Neptune are, or if those even exist. Anyway, you can download any kind of sound you want, and as you can see in my folder on my computer, I have already downloaded the sound, and I have my little patch right here. So if you have installed Sphere and if you have the sound itself, you can simply launch Sphere. There we go. You can go to File and you can go to Open, and you can navigate your way to the audio file that you want to analyze. When you choose this and when you click Open, it will give you some settings for sinusoidal partials analysis, and if you don't know what you are doing, which is okay, you can just leave these as it is, and if you're really into this, you can later figure out what these settings mean. But for now, I'm going to be clicking Analyze right here, and I'm going to get a very pretty picture as a result. Look at this, it looks really pretty, a bunch of lines, and if you have good intuition, you will probably know that these represent the sine wave partials, sinusoidal partials of the complete sound. In fact, if I press spacebar, I believe, Sphere is going to resynthesize, is going to recreate the sound by playing all of these sine waves together. Beautiful. So what we have just heard is indeed not the audio file itself, but a recreation of it using these sine tones. Now, why are we doing this in Max? Because while this app is super cool and super useful, it doesn't let us do certain algorithmic composition things that we can do in Max MSP. So, what do we need to do with this before we export the analysis? Well, you might have noticed that there are a bunch of lines, especially at the end. There is this whole just all these very, 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 very tiny sine wave partials, and well, I believe that these represent the white noise, background noise at the end of the sample itself, right? Also at the beginning, there are some partials that are not very strong. So in fact, if we try to take all of these partials and if we try to resynthesize all of these sine wave partials, we will probably need a few hundred oscillators, which might not be necessary to get the essence of the sound, what we perceive as the sample itself. So what you want to do is to go to Edit on Sphere and choose Select Partials Below Threshold. This is a very good trick to kind of filter out the unnecessary partials, or partials that are really, really quiet, so they don't really add anything meaningful to our perception of the sound file. So if I click Select Partials Below Threshold, I can choose here, okay, so select partials with maximum amplitude below minus 60 decibel. So select the really quiet ones, right? Minus 60 decibels is very, very quiet, but you can play around with this setting if you don't get satisfactory results. So clicking OK, there we go, they're all selected. Well, not all of them are selected, but the very quiet partials are indeed selected. So I can now press backspace to delete all of them. And we can hear the result again. Right, it sounds more or less the same, I believe, and I want to use this as the basis for my spectral synthesis. Alright, now that I've cleaned up my analysis, I'm going to go to File in Sphere and I'm going to choose Export Format because I need to export this as text partials. Right, it is possible to save this analysis as a format that is native to Sphere, and there are tools to load that in Max MSP too. But if we are going multi-channel, if we want to do multi-channel spectral synthesis, we want to export this as text partials. And after we select this, we can go to Export As, and there we go. We can just choose what to export this as, and I'm going to export this as coolanalysis.txt. Save. Okay. And then theoretically, we are done with Sphere because we have our analysis now, and we just now need to do the second step. We want to represent this analysis in a way Max will understand, and to do this, we have to first look at the analysis itself. This is a text file, right? So if I open this, I'm going to be led into the world of the matrix. This is the maybe the most intimidating part of what we are doing, which is to look at all these numbers, to be overwhelmed by the numbers, and to think, okay, well, what do these numbers mean? But it's easier than you think. It's actually much easier than you think. So at the beginning of this text file, right, there are a bunch of lines describing what this text file contains, right? So This is a text partials format. It has the point type of time, frequency, and amplitude. I'm going to get back to that in a few minutes. There are 83 partials. This is important, right? So I need 83 individual sine wave oscillators to resynthesize this. And then we have the partials data itself, right? So we have data itself of each partial. So we can use any kind of text editor for this, but first what I'm going to do is to delete the first few lines that describe what this text file actually contains, right? So I don't need to know what the format is or what the point type is or how many partials there are or the beginning of the partials data. I just need the analysis itself, right? So I'm just going to delete those first few lines, save this, and then I'm going to open this just to investigate it a bit better in Visual Studio Code. And again, you can use any text editor or a programming environment you want. I just want to look at, there we go, this analysis itself. And to make it a bit easier to look at, I'm also going to view on Visual Studio Code and choose word wrap, so that we don't have the lines going over and spilling to the rest of the screen. Now, if we look at this in this way, we can actually see that, well, there are all these line numbers, right? And each pair of lines follow a very specific pattern. We always have a short line and then a longer line. We have a short line and a longer line. We have a short line and a longer line. And indeed, these pairs of lines describe a partial each, right? So if there are 83 partials, I'm going to anticipate something like 166 partials. There it is. We actually don't need the 167th line. I can also delete this right here. All right, so what do these mean? Let's again try to understand what these numbers represent. In fact, I believe I can make this a bit larger if I zoom in a bit. Maybe that's not a bad idea, so that we can all see the numbers. There we go. Okay, so line 1. The 0 is the index of the partial, right? So this is partial number 0. Remember, we start counting from 0 in a lot of computer science things. 138 is about how many points that partial has. So how many times does the frequency and the amplitude of that sine wave change? So here we have 138 points in our partial number 0. Then we have the start time, which is 0 seconds, and we have the end time, which is 1.8 seconds, right? So we start playing this at 0 seconds and we stop playing this, we end with this at 1.8 seconds. Right? And then what follows, this very huge line, is essentially a description, right? A description of each of these individual, in this case, 138 points. And this is very important. This does look very intimidating, but actually these are in what we would call tuplets. These are always in groups of 3, right? So there's a group of 3, there's another group of 3, there's another group of 3, and so on. And each group of 3 describes a point's time. At which time does this point start? At which second does this point start? What is the frequency of this point? And what is the amplitude of this point? Right? And then again, for the next point, at which second does it start? What is the frequency of this point? What is the amplitude of this point? And so on. So regardless of which partial we are looking at, regardless of how many individual points there are in that partial, they all are simply groups of 3 numbers representing the second the point starts, the frequency of that point, and the amplitude of that point, right? And we want to go from one point to the other at a certain amount of time in our analysis. So that's essentially it for this text file. It is a bit overwhelming, it's a bit confusing, but we want to do a few things to, again, fulfill step 2, which is to represent this analysis in a way Max is going to understand it. And for this, we want to use the call object. Now, the call object has a very particular syntax, right? It expects the number, the index number of that collection item, comma, right? And then the numbers, essentially. I'm just writing a bunch of numbers, and then a semicolon at the end, right? And if I have the second entry in my collection, I would need to have 2 comma, and then a bunch of numbers representing the time, the frequency, the amplitude, whatever, and then a semicolon at the end, right? So in my text file, I need to essentially insert an index number at the beginning of each line. I have to put a comma after that index number, and at the end of the complete line, I need to insert a semicolon. If I can do all of this, then I am going to be able to simply load this into my call object. But furthermore, there's one more thing, right? There's actually a lot of fat, a lot of unnecessary fat in this text file in the form of these shorter lines describing what is going to happen, because I don't need to know if this is going to have 138 points. I can just look at this and I can count it, or I can use a counting algorithm to figure out if this has 138 points. I don't need to know when it starts and when it ends. Maybe in a future advanced spectral synthesis I will need this, but in this case I actually can filter out all of these shorter lines. All right, so more specifically, I can filter out the odd lines, right? So lines 1, 3, 5, and so on, and I can keep the even lines. And then I can just put a index number, comma, at the beginning of each even line, and at the end of each line I can insert my semicolon. Now, this is the kind of thing we can automate, right? And there are a few ways we can go around doing this. And on my MacBook, on my terminal, I'm going to be using the command line interface to do this in an easy way, but there are websites that let you do this, that let you import a text file and filter out even or odd lines, insert an index number at the beginning, insert a special character at the ending, and I'm going to be putting the links to those online tools, those websites, in the video description as well. But for my purposes, I'm going to open Terminal on my MacBook, and if you are using a Mac and following this along, you can do the same too. I am going to go up and I'm going to find my folder, the folder containing the text file. I'm going to right click it. I'm going to hold Option on my keyboard, and then I will have the option, when I hold Option, to copy this folder as path name. There. After I've done this, I can go into my terminal. I can type cd, short for change directory, space, and then paste the entire thing. All right, so now I'm in the folder. I have hacked into the system. I am in my spectral synthesis folder. So now I have to type in something very specific. I need to type in awk, awk, space, and then in single quotation marks, I have to type in nr modulo, or %2, equals 0. And then I need to type a pair of curly braces, and inside those curly braces, I need to type print ++n, space in double quotation marks, comma, space $0, space, double quotation marks, semicolon, and that should be it, right? We don't press enter yet. There's one more thing we have to do, but I believe, now I'm not a terminal or command line interface expert, but I believe what we are doing is we are asking the text file to check if a line is an even line, right? So if it's line 2 or 4 or 6 and so on, and if it is, it should write the index number, comma, the contents of the line, and a semicolon at the end. Anyway, after we have typed this, we type first the name of our text file, which is coolanalysis.txt. Right, let's make this a bit longer, or I guess not possible. Coolanalysis.txt, and then the larger than symbol, what I'm going to call as the larger than symbol, and then the file I'm going to write the results of this analysis, which is going to be cooleranalysis.txt. This can be any name that you want, right? This can be potato or tomato or cooleranalysis.txt. Okay, here goes nothing, pressing enter. There we go. Now in my folder, I have this cooleranalysis.txt. And if I open this, it does seem to be in the right format, I believe. Or is it? Let's open this as well in Visual Studio Code. Yes, beautiful. Look at this. Let's go to View, Appearance. Let's reset Zoom. And let's look at what we have. Also, View and Word Wrap is going to help us. There. Now we have each partial as an individual line in our text file. Each partial has an identifier, an ID number. It's 1 comma, 2 comma, 3 comma, and so on. And each line, therefore each partial, ends with a semicolon. right? So this is something call is going to understand. This is really cool because now we can simply implement this in Max, and then we can just find ways to play out this matrix-like data and actually get to the fun part of things. All right, so I have my cooler analysis.txt. It's in the same folder as my max patch, the spectral synthesis.maxpat. So I can do something cool. I can go to my call object, and as an argument, I can type in cooler analysis. And if I log the patch, and if I double click on this, I hope it's just going to open this. It's just going to open the text file itself because now this is loaded into call. Okay, so that was the second step. So now, again, the fun part, how do we resynthesize this using the multi-channel oscillators? And to do this well, let's try to understand what call does, right? So once you have loaded something into call, you can send it a number, right? And it is going to send out the corresponding information, the corresponding entry. Right, so if I type in 1 and send it to call, for example, guess what? I'm just going to get all those points, all those, how many was it? 135 points, these triplets of time in seconds, frequency and amplitude, and so on. Right, and the second outlet, that's also really useful, is going to send the index number. So if I send 1, it's going to be 1. If it's 2, it's going to be 2. So not very interesting, but this is going to be useful as well. The third outlet is going to send out a bang once it's done reading the data. And I think this is only applicable if we are reading the entire file, if we are loading a new text file. And the last one is going to be done when the output is dumped, right? And this is very important. Actually, we can send to call the message dump. And you know what it's going to do? This is really cool. It's going to send out all the information, all the entries in our collection one by one. This is really useful. So to demonstrate this, I can use a print object. Let's do this. So the first outlet of call goes to print. Let's look at our console. Let's lock the patch and let's press dump. And there we go. Now all the partials are one by one being sent out from call. And we can make use of this, right? So we can, in fact, use this to make a partial player. And let's try to do it like this. Before going into multi-channel things, let's just have a system where I type in the name of the partial, right? And I play out that partial in its entirety. Now, how am I going to do this? How am I going to play this out? Well, let's examine again the individual points of each partial. Right? Like I said, these are in seconds, frequencies, and amplitudes. These are groupings of seconds, frequencies, and amplitudes. And we do have an object in Max. We have a bunch of objects, actually, that takes in information that kind of looks like this and kind of generates a sequence of values that follow along the points, the points in this time period that is given. What I'm talking about is, of course, the line or the line tilde or even mc.line. Objects, right? These objects are super useful and super simple to use. You simply create a message that's like go to 0.1 in 1 second and then go to 0.75 in 2500 milliseconds and then go back to 0 over 5000 milliseconds, aka 5 seconds, right? So it's always the value to go to and the time it takes to go to that value in milliseconds. If I send line this message, in 1 second it goes to 0.1, in 2 seconds it goes to 0.75, and over 5 seconds it is going to go all the way back down to 0. So we can actually take all of this and we can interpret this data in a way that would make sense for line, and we can then use that to control our oscillators. But of course, since we are in the world of audio, since we want to do some kind of audio synthesis, I'm instead going to be using line tilde, which is the exact same thing, takes in the exact same kinds of messages, but it outputs an audio signal, right? So if I use the number tilde object, right? So this is the number tilde object. And if I make sure that my audio is on, which I can toggle through the EZDAC tilde object, I can do the exact same thing as in generating a signal instead of a simple floating number message. This is going to be extremely useful for us. So going back to this message, going back to this entire huge intimidating list, Well, we actually need two line tilde objects, right? We need one to control the frequency, right? So let's say this is going to control the frequency. And the second one is going to control the amplitudes. There we go. And I'm going to be controlling the frequency of a sine wave, right? So I can create cycle tilde, a sine wave oscillator, and anything that goes into its first inlet will set its frequency. Very easy. And if I want to play around with the amplitude, well, I just need to multiply the result of cycle tilde through the asterisk tilde object, the multiplication object, and then multiply it by whatever comes out of our amplitude line tilde object. Okay, so I just need to essentially take all of this, right? And I need to represent this data in two streams, one for the frequency and one for the amplitude instead of all of them together. So how are we going to do this? Let's think about this. We are working with lists, so anything I'm going to do is going to be using the ZL object, right? ZL object processes list in many ways. That's the official description, and there are a bunch of variations of this. ZL sort, ZL slice, ZL change, ZL compare, ZL delays. If you ever want to do things to a list, or if you ever want to do things with a list, you can always create the ZL object, right click, go to help file, and just look at all of these possibilities. And in my case, I first want to get these groupings of threes, right? And guess what? I believe there is a ZL.group object, and I can give this the argument 3, right? And if I take what comes out of call, if I put it through ZL group 3, and if I print the results, let's try this one, enter. Well, look at this. Now all of these points are being sent out in groups of 3s. All right. Now, what else do I need? Well, I need to take this list further apart, right? So I'm going to be using unpack 0, 0, 0. And of course, I'm making sure not to forget these dots after the zeros. So I'm going to get the time in seconds, the frequency in hertz, and the amplitude in amplitude, a value probably between 0 and 1. Now, if you are already good at this, you might have noticed something I'm kind of skimming around. I'm not really addressing it, and that is the fact that the time is being described in our Cooler analysis in a different way than what line expects. What do I mean by this? In my example with line, I always describe the amount of time that will take to go from the previous point to the next point, right? So go from your initial point to 0.1 in 1000 milliseconds, then go to the next point in this many milliseconds. Now this kind of contradicts with what Cooler analysis, or any kind of analysis through a sphere, contains, which is not the time it takes to go to the next point, but at which second from the beginning, at which second that point starts, right? So instead of saying it takes 1 second to go from the previous point to the next point and another second to go to the next point, it is instead, it should be saying, right, the point we want to go to 1000, the point we want to go to 1000, but instead it is going to say the point we want to go to is at 0 seconds, the next point is at 1 second, the next point is at 2 seconds, and so on. This is a bit tricky, and we need to essentially, each time we get the time, we need to compare it with the previous time. We need to manually, well, not manually, but algorithmically figure out how much time is going to pass between the previous point and the next point by subtracting the previous time from the current time, right? So if this is all confusing, just remember this. We need to take each second and we need to, from that, subtract the previous second. And that is going to give us the difference, aka the amount of time it will take to go to the next point. Now, there's a really cool way I like to do this in Max, which is to use the trigger object, TFF, meaning send the float first from the right inlet and then through the left inlet. And then to use the minus object and simply do what the Ghostbusters could not, which is to cross the beams, right? And I think this is going to work. I also need to give it the default argument 0 dots so that it works with float numbers. But you know what this is going to do? each time a number goes in, first we take that and from that subtract whatever was here before. After that is done, we take the same number and we load it up in the right hand side. This becomes the right operand. Next time there is a number, we subtract from the next number the previous number, right? What's going to be in here, and then again load this into the right inlet, the right operand right here. We just need to do one more thing. Well, these time points are going to be in seconds, but we are working with milliseconds, and it's very easy to convert between the two. Just multiply your time in seconds by 1000 and then do this operation, which is going to give us difference of time in milliseconds. Very useful. Okay, well, we need to do one more thing though, right? To make sure that this is going to make sense, we need to reset this right hand, make sure the right hand is 0 each time, let's see, each time a new partial is being sent, right? So each time call sends a new partial, we need to reset our minus object, right? So I'm again going to do something, let's see, L0 dot. I'm going to again use a trigger object, this time give it the arguments L and 0 dot, and I'm going to put it to connect it to the output of call, and then that goes into ZL group 3. And what is this going to do? Well, it is first going to send out the value 0, right? First the value 0 is sent, and I'm going to put that to the right inlet of my minus my subtraction object here. And after we set this back to 0, then we send out whatever list is in here going into ZL group. Right, so each time we are dealing with a new partial, each time we do a new partial, we are resetting our counter or difference finder algorithm back to 0. All right, now that this is done, what else do we need to do? Well, we need to have 2 buckets, right? So what do I mean by a bucket? Well, for each point, we need to collect the time and frequency, time and frequency, time and frequency, time and frequency, so that or frequency line till the object has the right kind of message. But we also need to do the same thing with the amplitude, this one right here, right? So time, amplitude, time, amplitude, time, amplitude, time, amplitude, and so on. Now, again, we have a little problem here. Now, this is something that might go over your head if you don't know the right to left nature of max, right? In max, everything is output from right to left. First amplitude, then frequency, then the time. But for our line object, we want first the value, then the time to get to that value, right? So first we want frequency or amplitude, and then we want to pack in the difference of time in milliseconds. So if I were to use pack 00, I would actually have a little error. I would either need to connect it like this and it would be out of order, or I would need to connect it in the usual way, but then I would need to swap things, which again does not make a lot of sense. So instead of pack, I'm going to use pack's distant but just as equally talented cousin, join. So join with the argument 2. You need to join 2 things. However, at triggers, the add triggers attribute, or the triggers attribute, lets us set which trigger is hot, which trigger is going to, well, which inlet, sorry, is hot, and which inlet is going to trigger the output. We start counting from 0, so inlet 0 is not hot, it is not going to trigger output. Inlet 1 is hot, it is going to trigger output. Right, so if I now do this, frequency in the first inlet, difference of time in the second inlet, then I'm going to get the combined message that is first the frequency, then the amount of time to get to that frequency. I can do the same for the amplitudes. I can take this, plug it in the first inlet, and then again take the exact same difference of time. Remember, these are all coordinated, and put that into the second inlet, and that is also going to give me the amplitude I need to go to and the amount of time that it will take me to go to that amplitude. Okay, so as you can see, this is a complex algorithm, right? We are dealing with intermediate subjects here, but I hope it's understandable. You're able to follow it along so far. In any case, so now we are iterating through all these points. For each point, we are generating 2 subpoints, one for frequency time, the second for amplitude time. But of course, we need to group these back together, right? And guess what? There is the object we have just used still available to us, zl.group, but this time I'm not going to give it an argument. zl.group is really cool. If you give it an argument, it will output the incoming values. Wait, it's not zl.group. What am I saying? I'm doing it wrong. zl, or was it zl.group? Yeah, it is zl.group. Okay, apologies, a little confusion on my end. If I do not give zl.group any arguments, anything it receives, any messages or lists, whatever it receives, it is going to pack it. It's going to collect it into one big list, and it is going to output it only when it receives a bank. Right, so we can simply put two ZL group objects here. There we go. Boop. And we can make sure that a bank is sent after the entire list of partials is processed. So the list of a single partial, after it's processed, this ZL.group should receive a bank message. And I can modify my trigger object right here, right? So I can make it so that it first sends out 0 like before to reset our time difference finder algorithm. Then the actual list is sent, triggering the entire operation. And once our list is done processing, so ZL group contains all the correct lists for our line tilde objects, then I'm going to send out the bank messages. There we go. And you can see I'm really doing my best to keep this tidy. It's really a challenge. Normally in personal use, in personal patching, I have different sessions. After I patch things, I take another session, right? There we go. I take another session where I just clean up the patch itself, but of course the best practice is indeed to, let's try to do it like this. There we go. The best practice is indeed to just do your best to patch things well as you are patching, but this could of course be cleaner. Okay, so ZL group is here, so now we should have the complete, there we go, pairs of things, pairs of values, one for my frequency line tilde and another one for my amplitude line tilde. Let's also make this look a bit nicer as well, and there we go. Right, and if I look at the resulting sound, I first want to use live.gain to make sure I can modify its loudness if necessary. I'm going to use limit tilde with the argument 2, a peak limiter, just in case I made a mistake and it's going to play something that is going to destroy my ears, and then the result goes into easy DAC. Beautiful. Okay, so there is just one more thing we need to do before playing this out, and we need to realize, people forget this, ZL objects have a default max size, and this max size is 256. Right, so if you have a list that is longer than 256 elements, it is going to be a bit confused. And it could be in these kinds of spectral analyses, not always, but it could be that the incoming list is greater than 256. So I always prefer to give every ZL object I use in my spectral synthesis algorithms the ZL max size attribute set to 99999, even though that's larger than the theoretical maximum limit, just to tell myself and the others that this ZL group is as large as it gets. Right, so any ZL object you have should have the ZL max size attribute set to 99999. Okay, now comes the moment of truth. Let's see if we are going to hear anything. Partial 1. Yes. Partial 2. Yes. 3. Partial 4. 5. These are little beeps, right? But you have to imagine these are all tiny partials that will come together to create a really cool, complex sound. This one's a bit loud. Beautiful. Okay. Really cool. So you can already use this, right? You can just take the individual partials of a sound analysis and use that to create a soundscape, a spectral soundscape, or use as a basis for other kinds of sound design and composition. But I think we can go further. And one thing I noticed while we were kind of going through the partials is that there is something in the data. I don't want to go over it right now, but not all of these points end at 0 amplitudes. Right, so maybe we should make sure that the final point in our line always ends with a value of 0. Right, so I want my amplitude to be 0 at the end. And what can I do for this? Well, I guess I can do zl.join. And I can give zl.join the arguments, let's say 0, 100, make sure to give it the zl max size attribute set to 99999. And what is this going to do? It's going to take whatever list of points we have for our amplitude line, and it will add to that 0, 100. So go to 0 over 100 milliseconds at the very end. So once you are done, just make it quiet. All right, so now we should have our beautiful partial player. Beautiful. This is probably the ringing part of our bowl. All right, now let's do the final step, which is to turn this into an MC oscillator method of synthesis so we can hear all the partials all together. Well, what do I need to do is pretty simple. Then I just need to create the MC dot equivalence, not OC, but MC dot equivalence of all these objects: MC dot line, MC dot cycle, MC dot multiplication. And then if I'm going to use live gain and my stereo outputs, whoops, didn't mean to delete that, I then need to go to MC dot mix down, right? I want to mix it down to 2 channels, and I'm going to give the attribute auto gain set to 0. I do not want to manipulate the amplitudes of the individual channels because these partials are created to be played together, right? So I do not need to use auto gain here. And then I can simply use mc.unpack with the argument 2 so that I get 2 beautiful singular audio channels that I can play out through live.gain. I also need to tell mc.line that it is going to have, how many was it? 83 channels, right? So it's going to have 83 channels at chance attribute set to 83. And this is really useful. Then all the objects, all the multi-channel objects, the 83 multi-channel objects is connected to are going to also have 83 channels. So I do not need to tell MC cycle and MC multiplication that it needs to have 83 channels. It knows because MC.line is sending these objects 83 channels. Okay, now the question is, well, how is MC.line going to know which one of these channels it needs to send our list of values, right? Because if I trigger the, let's say, the 7th partial, then it should send this to the 7th channel and not the first or second or a random channel or all of the channels. Well, guess what? You will be shocked to hear this. There is actually also an MC object that helps us target specific channels when we are sending messages to multi-channel objects, right? So if I connect the output of my zl.group to mc.target, and if I connect the output of that with MC line, it is actually going to create a very specific message automatically, algorithmically, that lets MC.line know which channel should receive this message. To make this work, I only need to send the target index, so the number of the channel, an integer number, to the second inlets of the MC.target objects that I have here, right? And guess what? Guess what I said at the beginning? Remember the second outlet of call, or this number here too, but I prefer to use the second outlet of call. It is going to send out, right? It's going to send out the number of the collection element I'm pulling, right? So if I call the first partial, this is going to be 1. If I call the second partial, this is going to be 2, and so on, meaning I can take the index number of my partial and I can connect it with MC.target right here. There we go. All right, so now when I trigger each partial, it will tell MC line which channel to target, and then it's going to send the right message to there. So now comes the moment of truth. Now I'm going to save my patch and I am going to click this dump message here. And if everything works well, all of the partials will be dumped at once. I'm going to hear an approximation, right? So we're not going to be perfect, but I'm going to hear a good approximation of the bell sound. So here goes nothing. Okay. Interesting. So we seem to have a little problem here, which is that... Oh, I know what the problem is, I believe. Wait, let me try something. I think MC.line also needs to know how many points it can maximally take. Let's try this again. There we go. Beautiful. At the beginning, you might have heard this like little ramping up the frequency. That is because, well, the MC.line is continuing from where it has left off, and that is something we can also change down the line. But right now, this is really cool. I have this dump button, which triggers this bell sound, which is actually a resynthesis of the sound itself, created through a bunch of sine wave oscillators. Beautiful. So how can we play around with this? Well, there are a few ways, and I'm going to show you, let's see, maybe 3 of them. So one thing I can do is to use the MC.deinterleave tilde objects, and it's going to take a multi-channel audio signal, and it's going to deinterleave it in 2 outputs or 3 outputs or 10 outputs, depending on which arguments you give. And what does deinterleave mean in this case? Well, if I have 83 channels, it's going to send here the first channel, second channel, third channel, fourth channel from the first outlet, the fifth channel from the second outlet, the sixth channel from the third outlet, and so on. So I'm going to have 1, 4, 7, 10, etc. These channels from the first outlets, right? If my maths is not failing me, then 2, 5, 8, 11, and so on from the second outlet. And I'm going to get the channels 3, 6, 9, 12, etc. from the third outlet, right? So I'm like thinning out the partials essentially in different ways to achieve different timbres. I'm taking all my partials and I'm deinterleaving it into different collections of partials for a more specific kind of sound. This is the first group. Let's try the second group. Ah, beautiful. It's a bit more muted. Or the third group. Ah, now that's really thin. It's a beautiful, thin sound. Right, so you can definitely experiment with the deinterleave object to play around with the results. Another thing we can do, let's see. And there it goes. Another thing we can do is, it wasn't mc.unpack. What was it called? Let me do a little search here. mc.separate. There it is. mc.separate is another object we can use. So this is pretty much like mc.deinterleave, but we can just tell mc.separate, well, first give me the first 10 multi-channel signals, then give me the next 30 multi-channel signals, and then give me the next 15 multi-channel signals, and then give me the next 20 multi-channel signals, and so on, right? So I'm separating the incoming multi-channel signal into 10 pieces, and then 30 pieces, and then 15 pieces, and then 20 pieces. So again, a great way to target specific range of partials in your analysis. For example, the first 10 partials are like this. And these are the next 30 partials. Beautiful. Right, the result is a bit similar, but we again get a very subtle play with timbre. And the final thing we can do, this is really cool, why don't we just get rid of the amplitude envelope itself? I actually do not want to trigger the amplitudes of these partials, but instead what I want to do is to take the frequency of these sine waves, which are constant, and manipulate the amplitude myself using basis functions. Okay, this is slightly advanced, but bear with me here. I'm going to dip my toes into the world of jitter. I'm going to create the object jit.bfg, and I'm going to give it these specific arguments. Let's see, 8322 float, wait, what am I doing? No, jit.bfg 1 float 32, 8322 at basis noise dot simplex. And then I'm going to take the output of this jit.bfg and I'm going to put that through a jit.matrix that is 1 float 32, 83. And then I'm going to create the jit.p window object to visualize the results. Jit.p window. Now if I send it back to jit.bfg, what do I get? I get this little gradient. This is actually a procedural noise that is 83 cells long, right? 83 individual values that use procedural random noise that have more or less a range of -1 to +1. I can actually send this the message offset $1 0 0 comma bank, and I can send a number here. There we go, to kind of scroll through this list of values. It's going to generate some random visual patterns. I can also send this scale $1 $1 comma bank. Actually, it's not necessary. Scale $1 comma bank is enough. I can connect, there we go. And I can again change the scaling. So how detailed is this noise, or how not detailed is this noise? I can again play with the offset here. And while this looks really cool visually, I can then use the object jit.spill to take this matrix and turn it into a list of, there we go, 83 elements where they are between more or less -1 and +1. Before I send it to jit.spill, I can use jit.clip with the attribute min set to 0 to make sure anything less than 0 stays at 0. Why am I doing this? Because I want my amplitude to not go to lower than 0, right? I want my 0 to be my lowest amplitude. There we go. Beautiful. And since I have this list here, I can use the object mc.list tilde with the argument, I believe, with the attribute chance set to 83, so that this list I'm sending is converted into an 83 channel multi-channel audio signal containing these values, right? So look at what we are doing here. This is super cool. We are taking something visual, something that belongs to jitter. We are using that to generate these cool patterns. We are manipulating it so that it turns into a list and then into a multi-channel signal so that the amplitude of each partial is not determined by its envelope, by the envelope of the partial, but instead it depends on these random values, random visual patterns I am generating through jit.bfg. So let's see if and how this sounds. Oh, beautiful. Though if we do this, right, we have to make sure mc.mixdown has its auto gain set to 1. That is really important because now all these partials are not meant to be played together. We are forcing different amplitudes on them to get new sound results. And now I can change the offsets. And I'm going to get all these different combinations of frequencies. Beautiful. So while this is by no means perfect, there are a few aspects missing here that does not make it complete spectral synthesis. It is a good enough approximation and gives us a lot of material to work with in sound design and in composition, and using the individual partials of a sound, of a sample, where we can target them individually and we can create new things, new sounds, new approaches, and even new algorithms from their individual profiles. I think this might be the beginning for a lot of cool new pieces and techniques and instruments and so on. And we even had a taste of some visual applications here as well. So I hope you have enjoyed this. I hope this was informative, and I really hope you can create something really cool using this. In the meantime, thank you for watching.